All right, this is round 2 of the video. First one did not go as planned. Made it to slide 8 and made a glaring mistake. So hope this one goes better. So here we go. I hope you guys are having a good day today. This is the second section of chapter 2 where we're talking about limits of a function. We introduced the idea with the tangent and the velocity problem. We set up some problems that look something like this, and where we got values that were closer and closer together. In this case, it says I'm taking values that are closer and closer to 2. And what I'm looking for is the value of f of x, that whenever I plug in these values that are getting closer and closer to 2, what these values of f of x are getting closer and closer to. And it looks like it would be a 4, right? And we picked a side. We picked the left side or the right side. We went a little bit less than 5 or a little bit bigger than 5, if I remember correctly. And it doesn't matter which side we pick. If I get closer to 2 on these x values, I see myself getting closer and closer to 4 on these function values. Okay. So let's talk about what's going on with this. So we express this by saying, we say that the limit of the function f of x is equal to x squared minus x plus 2 as our x approach to that is equal to 4. It's a lot of words there. The limit of the function as x approaches to is equal to 4. Now, I switch around some of these I think they're called propositions. The prepositional phrase. And so sometimes I'll say the limit as x approaches to. Sometimes I squeeze it in right there of the function. So it doesn't really matter what order you say it in. If you put the as x approaches to first, it's all going to come out the same. Okay. Now we have a notation for this, so we don't have to write this out every time. So we can simply write the limit of the function x squared minus x plus 2 as x approaches to. And notice how x approaches to is an x arrow 2, and it's kind of smaller, and it just fits right there underneath that limit. And then is equal to 4 stays the same. So that's how we write it. Let me formally introduce it. Okay, formally introduce it. And I'm not going to write it all out again. I'm not going to do the we say. But what we write is just pretty much the limit as x approaches a number. Since I don't know what that number is in this case, I'm going to leave it generic. I'm going to leave it just as a in this case. Of a function is equal to the limit. Okay. And like I said, we say the limit of a function as x approaches a is equal to L. And we say that if we can make the values of f of x be arbitrarily close to L. So what we saw a while ago was that f of x was getting close to 4. What's close to 4? Well, let's say 3.99 is pretty close to 4. It's just however close you would like to get it. And we did that by making it so my x got sufficiently close to a. So x was getting close to 2 a while ago whenever I was able to find that limit was 4. Now here's the thing with calculus, is that it doesn't have to be equal to a. A lot of times I can plug in a and it's going to be the same as the limit. We call that a well-behaved function. But it does not have to equal a. It can equal a, but it does not have to. And so down here at the bottom I have an alternate form for writing a function. I will not use this unless I have to, but I think a couple times they might write it out like this in the book. It's not wrong, it's just kind of a longer way of writing it. So let's talk about how we're going to find this. You guys are probably anxiously awaiting slide 8 to see if I make a mistake again. All right. Tell you, if I make another mistake, I'm just closing it up and going home. I'll try again tomorrow. But I'm wanting to guess the value of it. I hate that word guess. All right. I guess we're saying guess because this isn't the best way of finding exactly where it can be at. This is a good fallback to always use if none of your other methods work. It's kind of like factoring. Factoring helps me find an answer really quick. But if it doesn't factor, or if I forget how to factor, I can always go back to that old quadratic formula to solve a quadratic equation, where if it doesn't factor, or if I just forget how to. So this whole lesson right here will be about the fallback. And the fallback is going to go all the way back to making a table. And so whenever I make this table, I'm wanting to put whatever x is approaching right here in the middle. And on either side of that 1 that I put right there on that top x column, or top x row, I'm wanting to put values that are close to 1. Well, what's close to 1? I would say like 0.999 is close to 1, and 1.001 is close to 1. And I have it so that my horizontal table here goes in numerical order. All right, so the 0.9 is going to be way over here, and then I have 1.01 and 1.1 on this side. Once I get this set up, I got all these values up here that are getting closer and closer to 1 as I come in from the sides. What I want to do is I want to take this 0.9 and I want to plug it in for both of these x's right into my graphing calculator or a regular calculator. If you can use that table feature on your calculator, it'll cut out a lot of work. And if you have questions about that, be sure to ask me on our review day. I'll be glad to show you that because it will really help out. So I'm going to plug in 0.9. I got 0.5263. That number by itself doesn't really get me anywhere as far as seeing what value I'm getting close to. So I added a 9 to it. I got 0.50251. Okay, I'm pretty sure this thing is getting closer to 0.5. I can be more sure about it if I plug in one more 9 into this. I get 0.5003. I'm feeling much better about getting close to 0.5. Me working the other side of this is a great way to check my work, because whenever I plug in 1.1 in for these x's, I got 0.4762. Okay, when I plugged in 1.01 in for the x's, I got 0.4975, and then 0.4998. And so as you can see, these values, these f of x values, if I got closer and closer to 1, I'd like to point out that if I was to actually plug in 1 into this, I would get 0 over 0. It's called an indeterminate form. We're not ready for that yet, but I get something that's not defined. So plugging in 1 does not work with it, but calculus lets me know, this idea of limiting values lets me know that if I take the limit as x gets close to 1 of this function, my values are getting closer and closer to 1/2. You can definitely call it 0.5 if you want to. I would be fine with that if this works. All right, let me show you that again, and then I'll turn you loose on an example. Now, the limit doesn't have to approach 1 every time, like at that one. We approached 2 earlier, I believe. This one approaches 0. So 0 is going to take that middle position right there on that top row. Now I want to get close to 0. Okay, close to 0. If I start over here on the left, that's going to be like negative 0.1, negative 0.01. Just keep adding zeros to it until I get something really close to 0. I think if I do a little bit of math on this, I think that this turns out to be an even function. Okay. Now, first of all, plugging in 0 is not going to get me anywhere. It's going to give me something that's not defined. Okay, but I have an even function here. I can easily tell because both of these guys are squared and the rest are numbers. So if I plug in a negative t, it quickly comes back out to this function. So whenever I plugged in a negative 0.1 for this, let's see, what did I get? I got 1.6662. It's going to be kind of hard to figure out by itself. So I'm going to add a 0 in there, get a little bit closer. I got 0.166. I'm getting closer to 0. So let's add another 0 in there. I get 0.1666. How many sixes did I get there? Like 5 of them or so? I didn't move very much to go from here to here. And I end up getting the same thing on this side. I think this is just 6 repeating again. And 1 point. That's weird, that's a 1 right there. You might check my math on that. 1.6662. Really, I'm kind of far away from it at that point. And so if I look at this, as I get closer coming in, I do get that the limit of this function, it's not actually going to be 0. It kind of froze itself right there at 0.111116 repeating, which would just, not as bad as the mistake I made a while ago, trust me. All right, 0.16 repeating, which would just be my fraction of 1/6. All right, now it's your turn. You're gonna set up your table. I'm gonna give you a hint. Make sure your calculator's in radians. If not, it's gonna look weird. So you're gonna want to use radian values on this. Set up your table. I guess I could have left my zeros alone on top and use those same values that we just did. Anyway, you're going to pause the video. I'm going to hit pause. We're both going to work it. We're going to come back and we're going to have the same limit. It's going to be a beautiful thing. I'll see you in just a minute. I got 1 on it. It went to 1 really quick. We like those. It makes us feel better about our answer, especially when they come out to be those nice whole numbers. Okay. Now, I want to point out the graph of this. If I was just to, I'm just going to do a rough sketch of the graph. I have it up here. And so, as you can see, if I plug in 0, I get something that's not defined right here. And that's because right here, there's going to be a hole. And as I come in, I'm getting closer and closer to that hole. Again, so while this value at 0 is not defined because there's a hole right there, as I got closer and closer to this value from both the left and the right side, I was really close to the function value of 1. Okay, so that's why all this works graphically. We're going to be looking at that more later in this video. And I'm not going to erase my X column this time. So let's plug in these values. I sadly don't have these values. Actually, let me just change this. I'm just going to do some different values here. So I'm going to use like 1.5. I'm just going off what's on my notes so I can have the answers right there. We might do this in class a little bit differently. We'll probably just use those values that we had up there. But if I plug in any of these values, I see that they're all going to be 0. So it really looks like as I get closer to plugging this in, plugging in 0 in for X, it would be 0. But it's actually not. Actually not. And so in order to show you this, I'm going to need to pull up my graphing calculator. I looked through this and I thought that I had only one graphing calculator problem. So you're going to have to bear with me for just a second while I want to make sure I am in radians, which I was not. That would have been a disaster. But I am going to do sine, what was my problem? Sine of pi over x. Close parentheses, delete. Always works best if you hit clear before you do anything. I think this is it. So I'm going to hit graph on it. Don't mind that little purple dot. Can you see what's going on right there in the middle? It kind of wiggled around a little bit. It didn't really happen to come in right at 0. I'm gonna zoom in on that origin right there. I really want you to see this. It actually, the graph looks like it's going crazy right there in the middle. My exact words I like to use on that is that the graph is oscillating wildly. All right, and you're not allowed to do that when you're taking a limit. It must approach that number smoothly. And so, since the graph oscillates, it's okay for it to oscillate, just can't oscillate wildly. Since the graph does that, let me move that cursor so you can kind of see it. Anyway, people have had a lot of fun with this, and the more you zoom in, the crazier this graph gets. But it's okay for the graph to oscillate between -1 and +1, like you see it doing. You just can't do so wildly. So, what does that mean for our answer? Well, in this case, I know it's not equal to 0. I'm not going to be able to find the limit of this function. And because it oscillates wildly like that, it must approach it smoothly. And so in this case, all of you mean girls, people will love this. The limit does not exist. All right? The limit simply does not exist. We cannot find it. Now there's some other tricks that I have too, where it's kind of hard to find the limit, and we realize we need a better way to do that. And that's what's going to be coming up in a following video or following videos. Better ways to find limits of, say, this function right here. Okay. I'm going to skip this problem, but we will have worked it in class. We don't need it for in order to work the problems that are at the end of this video. I want to talk about one-sided limits. One-sided limits. So I have this piecewise function. I'm going to go ahead and graph this piecewise function. It's a very basic piecewise function. It's actually, come to find out, a very popular piecewise function. It says h of t equals 0 if t is less than 0. So I can graph that. 0. Oops, I don't want that to be close. It needs to be open, don't I? I guess I have to load the mistakes I made. Okay, and it equals 1. We're up here. And that's what this function is. And so this is known as the Heaviside function. I just thought it was called Heaviside because maybe this side was a little bit heavier. But come to find out, oh, I don't want to close caption. I can, that'd be pretty cool. Come to find out, after a quick Google search, there's a guy named Oliver Heaviside that this function is named after. He was an electrical engineer, mathematician, and physicist who did some work in calculus. I pulled out one of my old history of mathematics books, and he did some work with some of the early people that came up with calculus and did some work with calculus. And neat thing to look into, not really in the scope of this problem, but it's actually named after a guy by the name of Oliver Heaviside. Good to know. It's really good to know. So this is my function. And so two different things are happening I want to show you on this. First of all, as t gets closer, here's my 0 right here. Okay? As t gets closer to 0 from the left, okay, we say as t approaches 0 from the left, then the Heaviside function gets close to 0. Whereas, if I was to come up here, and as I get closer to 0 from the right, again, I'm not worried about what it's equal to or what it's not equal to. I'm interested in what value I'm getting closer to as I come in, as t approaches 0. I forgot to put from left. And so as t approaches 0 from the right, I see that this Heaviside function is getting closer and closer to this value right here, 1. And so if I think back to my definition, it says that I have to come in to equal a unique number right there in the middle. So since it does not approach a single number here at 0, then I would say that the limit, as I guess it'd be t approaches 0 of the Heaviside function the limit does not exist. So that's another way to show that the limit does not exist. It can oscillate wildly like we saw in the last example, or it can just come in at two different values from the left and the right. Now, while the limit does not exist, we are able to break this down a little further. Okay? And so this top blue up here, we have a way of writing as t approaches 0 from the left. Okay? So the way that we would write that, we'd say the limit as t approaches 0 from the left. I put a little minus sign up there. It means that it's approaching 0 from the negative side. And so while the limit does not exist, we call this a one-sided limit. The one-sided limit does exist in this case. And in the same manner, we can take the limit as t approaches 0 from the right of the Heaviside function, and it equals 1. And so the limit does not exist, but the right hand and the left hand limits oftentimes will exist. And so we can break down a limit even further into left hand limits and right hand limits. So I've got to formally introduce this now. This is a good spot to take a break. If you're needing a drink, go potty, you want to push this off till tomorrow, this would be a good time to take a break, because this again is a 2-day lesson, and I'm about halfway. I hope I'm more than halfway through it. Looking at it, I'm probably more than halfway through it. But we are able to write, I'm going to do the left-hand limit first. The limit as x approaches a from the left of the function is equal to L. And we say the left-hand limit as f of x as x approaches a, all right, is equal to L if we can, again, make values of f of x arbitrarily close to L by taking x to be sufficiently close to a. But in this case, x has to be less than a in order to use a left-hand limit. Less than left hand. Less than left hand. I need to go through and do right-hand limit on the same slide. Oh, we are just going the wrong way. So, in the same way, we can do a right-hand limit using this same definition right here. The limit as x approaches a from the right. And like I said, we call this a right-handed limit as the x approaches a from the right. Again, the same wording all the way through until we get right here. We need to go greater than a, for the same reasons that I just showed you on the Heaviside function. Okay, so both of these have been introduced, and I like introducing both of these because now we get such a better definition of a limit. All right, so yes, I already did that. So now we get a better definition of a limit. So now we can say the limit as x approaches a of the function is equal to L if and only if the limit as x approaches a from the left of f of x is equal to L. Let me do a big and in here because this also has to be true. The limit as x approaches a from the right of f of x has to equal the same number L. Has to come in smoothly and meet that same number. Let's make sure we know the difference between these. Okay, so I've got a graph down here. And I'm wanting to find these limits if they exist. All right, I'm going to do A, B, and C. You're going to do D, E, and F. Let's do A, B, and C together. So I'm doing the limit as x approaches 2. Let's see, my g of x is the whole blue line. So we don't have two functions here. It's just one nasty piecewise function. The limit as x approaches 2 from the left of g of x. All right, so 2 from the left. Here's 2. As I approach 2 from the left, I see that my function value is close to 3. Let's approach 2 from the right. As I get closer to 2 from the right, see my function values down here at 1. And so what I'm able to conclude now, using my new definition of a limit, since my left-hand limit and my right-hand limit are not equal, then the limit as x approaches 2 simply does not exist, because they have to come in to the same value. Whew, a lot going on there. Try the limit as x approaches 5, left and right, and add it, and see what you come up with. Okay, I'm going to write my answers down, and then hit pause and then unpause once you're done. Two, 2, and 2. Came in from the left at 2, came in from the right at 2, and then this same number has to come over. Some of you are thinking, well, man, I put 1 right here. Nope, it does not equal 1. Now, if I was to ask you g of 5, that would equal 1, but that's algebra. I'm interested in calculus and limits and what the value is getting close to, not necessarily equal to. So be careful with that. Infinite limits. Infinite limits are just going to be limits that don't exist because they don't approach a unique number. They're going to go up to infinity. Let me show you an example right here. Example 7. I'm wanting to find the limit as x approaches 0 of 1 over x squared. Like I said, we will get better ways of doing this where we're not making this big table. But I'm just going to fall back on the table for now. I'm going to get closer to 1 on both sides. You can see you're thinking, man, he's already used these numbers. I have. These are very good numbers to use. That's why I don't talk whenever I'm trying to write. I always mess up. These are very good numbers to use whenever x is approaching 0. Okay. So if I plug in 1 in here, again, I got an even function. So whenever I plug in 0.1 and negative 0.1, I should get the same answer. And I do. I think I got 100 on there. Doesn't seem too bad. Might be approaching 100, maybe 200. Okay. Negative 0.1 and positive 0.01, I got 10,000. It got big really quick. And I don't even have enough room to write the next one. It's going to be 1 million. This thing is not coming down anytime soon. Okay? And so the way that we write this, it is, I don't think it's necessarily wrong to write infinity, but you need to also put out there that the limit does not exist, because infinity is not a unique number. It's not a number. It's an idea. Okay? And so I would like to see infinity and does not exist on problems like this. Let me show you what this is going to look like in the graphing calculator so you can have a visual with it as well. So let's get rid of that messy thing and go 1 over x squared and graph. As you can see, let me expand that so you can see it. As you can see, we need to zoom out as well. Zoom out from there. And I got that purple box right there. Now, as you can see, as I got closer and closer to 0, this thing, we say it increases without bound. It just goes up. It's finally probably going to connect somewhere way up here at infinity. Right? So it works kind of like a vertical asymptote. It is a vertical asymptote right there, but we never quite reach it. We can't ever touch this line. We just get really close to it. And so that is what it will look like. I think I'm done with my graphing calculator for this video. Okay, so let's formally introduce ourselves to this. Let f be a function defined on both sides of a, except possibly at a. Then, if we get the limit of the function as x approaches a to equal infinity, that means that the values of f of x are getting arbitrarily large. We got large. We got up to 1 million. If we were to get even closer to 0, it would grow even more than 1 million. If we take x to be close to a, and we were taking x to be close to 0, not necessarily equal to a, though. And in the same way, we can do the negative side as well. If we let f of x be defined on both sides of a except possibly at a, then we can also go down to negative infinity. It means the value of f of x is made arbitrarily small as we please. So we could have gotten negative 1 million, negative 1 billion if we would have thrown a negative in there in the right spot by taking x to be sufficiently close to a. Still, either way, whether we get infinity or negative infinity, the limit's not going to exist. But I want you to denote to me whether you're getting infinity or negative infinity. Okay, I've already done that definition. So here we go. This would be a good example of us, the same example that we just did with our x's and f of x. We throw 0 right here in the middle, and really don't want to make the whole table. It'd be the whole table again, except for this time, whenever I was at negative 0.001 and positive 0.001, I would be at negative 1 million. Okay. And so we say this decreases without bound. As I got closer to 0, the numbers were just getting incredibly small, away from 0 on the negative side. And so I would get negative infinity, where the limit actually does not exist. So what could this look like visually? Because these are going to help me get vertical isomtopes eventually. So what does it look like visually? I could have, say, a vertical isotope right here. This thing could be motoring along, and then it just comes up right there at, let's say, A. And so on this one, this would be a one-sided limit. The limit as x approaches A from the left of whatever this function was would be equal to infinity. It could be minding its own business right here, and then, woof, come flying down. In this case, the limit as x approaches A from the left of the function would go to negative infinity. Let's just throw, and this is going to be where A is, where this isotope is. We could go from the right side as well. I think you know where I'm going with all this. And my colors won't match. It's okay. But suppose A is right there. I get the limit as x approaches A from the right of whatever function this is would be infinity. That's going to denote, it's going to tell me that there's going to be a vertical isotope right there. And so the last way you'll see this written, the limit of the function as x approaches A from the right could also be negative infinity. So anytime you're approaching this function from the left or right and you get infinity or negative infinity, that is going to let you know that we are looking at a vertical isotope. Okay. And that's actually going to be my definition of a vertical isotope. I hate to move this stuff. So we have the line x equals A is called a vertical isotope of the curve if at least one of the following statements are true. All right, so if any of these statements down here are true, then we're good. We're going to have a vertical isotope. Okay. We're going to expand on that later on. You might not see a lot with that tonight. All right. What I do want to show you is maybe a shortcut where you don't have to make a table. I'm going to kind of let you in on how my mind kind of works these infinite limits. So let's pull this one down for a second. Whenever I think of x approaching 3 from the right side, here's what's going on in my, I'll make a thought bubble. Draw bald Mr. Lovelady here. Really tired. He's thinking, how's that go? Bigger bubbles, there we go. Here's what he's thinking. He's thinking, man, if I could just plug in something really close to 3 on the right side, that would be like 3.001. Oops. That would be like 2 times 3.001. Okay. Now, my second thought bubble on this is thinking, man, that numerator is getting really, really close to 6. And the denominator is so small. All right. So my second thought bubble on this is I was really close to 6. And this down here was something really small. But still positive. I'm trying to keep track in my head if it's going to be a small number that's really close to 0 that's positive, or a small number that's really close to 0 that's negative. And so in my calculator, I can type in 6 divided by 0.0000001, something really small. But if I take 6, or any number for that matter, and I divide it by something that is incredibly small, like 1/1,000,000th, think about what that would do. Is I would be taking the reciprocal of the 1 over 1,000,000. I would be taking 6 times 1,000,000. And what that would do is it would make it so this limit blew up to infinity. So let's think about what happens in my thought bubble over here on this side. If I take the limit as x approaches 3 from the left, again, if I plug in 3 in from the left in for that x, that's going to be 2 times, let's see, 3 from the left would be 2.99999. Now that might look like it's hard to do, but again, I'm going to be really close to 6 if I multiply that out. And then 3 from the left on the bottom would this time give me a negative number. So let's think about this. On top, I've got something really close to 6, and on bottom, I have something really close to 0, but on the negative side. So now my thought bubble changes to, well, I'm still close to 6, but then I have small that's on the negative side. So like negative 0.00001. And luckily my rules for division still work. I've got a positive divided by a negative, so my answer is going to be negative. And I still have 6 divided by something incredibly close to 0 is going to blow this number up. Or blow it down, if you're thinking about it going down to negative infinity. I'm not going to worry about these vertical asymptotes of tangent today. I'm just going to go ahead and cut the video off here. But here's the assignment. Work on some of these. You're going to have to make a lot of tables. And so, like I said, though, it's a good fallback, and I promise you'll be making tables soon on an assessment. Let me know if you have any questions. Have a good rest of your day.